Imagine looking up at the night sky. Thousands of stars glitter above, the moon traverses its path. It seems obvious, doesn't it? Everything revolves around us. For millennia, this geocentric view dominated human thought. It felt intuitive, it felt real, and it was completely wrong. How did we break free from this Earth-centric perspective? It was a long and arduous journey, fueled by curiosity, observation, and the revolutionary power of scientific inquiry. Over centuries, courageous thinkers challenged established dogma and reshaped our understanding of the cosmos. We embarked on a voyage from geocentrism to a universe far grander and more mysterious than our ancestors could have ever imagined. In the 2nd century AD, the Greek-Egyptian astronomer Claudius Ptolemy codified the prevailing geocentric view. His model, known as the Ptolemaic system, placed Earth firmly at the center of the universe. The sun, moon, and stars, he argued, all moved in perfect circular orbits around our world. Ptolemy's model wasn't just a philosophical concept, it was a complex mathematical framework. He incorporated intricate systems of epicycles, smaller circles within larger orbits, to account for the observed motions of the planets. While successful in predicting celestial events with reasonable accuracy for its time, the Ptolemaic model remained fundamentally flawed. It would take over 1400 years for a truly revolutionary idea to emerge. In the 16th century, a Polish astronomer named Nicholas Copernicus dared to challenge the established order. In his groundbreaking work De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, Copernicus proposed a radical concept, the heliocentric model. The Earth, he argued, was not the center of the universe, but merely one of several planets orbiting the Sun. This revolutionary idea didn't immediately shatter the geocentric worldview. Copernicus's work was initially met with resistance and skepticism, particularly from the Church, which held the Earth-centered view as dogma. But the seeds of doubt had been sown. The heliocentric model, with its elegant simplicity, began to slowly chip away at the foundations of the old cosmic order. Copernicus had shifted the cosmic stage, dethroning the Earth from its central position. However, it was the German astronomer Johannes Kepler who refined the heliocentric model, providing a more accurate description of planetary motion. Kepler, using meticulous observations made by his predecessor, Tycho Brahe, discovered that planets don't move in perfect circles as previously thought. Instead, they follow elliptical paths, with the Sun at one focus of the ellipse. Kepler's laws of planetary motion, published in the early 17th century, marked a turning point in astronomy. They provided a precise mathematical framework for understanding how planets moved within the solar system, solidifying the Copernican revolution and paving the way for a deeper understanding of the forces at play. While Kepler described how planets moved, it was Sir Isaac Newton who answered the crucial question, why? Kepler's laws of planetary motion were groundbreaking, but they lacked an explanation for the underlying forces at play. Newton's work provided the missing piece of the puzzle. In his monumental work Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy, published in 1687, Newton unveiled his groundbreaking universal law of gravitation. This work laid the foundation for classical mechanics and changed the course of science forever. This law stated that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This elegant equation could be applied to everything from apples falling from trees to the orbits of planets. Newton's law of gravity was a game changer. It not only explained the motion of celestial bodies, but also had practical applications on Earth. Engineers, architects, and even artists began to see the world through the lens of Newtonian physics. It provided a single, elegant explanation for why objects fall to the Earth, unifying the motion of everyday objects with the motion of celestial bodies. Why the moon orbits our planet, creating the tides and influencing the natural rhythms of life on Earth, and why planets remain in orbit around the Sun, maintaining the delicate balance of our solar system. It was a unified theory of motion, connecting the heavens and the Earth in a way never before imagined. Newton's insights bridged the gap between the terrestrial and the celestial, offering a comprehensive understanding of the universe. Newton's law of gravity reigned supreme for over 2 centuries, explaining a vast array of phenomena with remarkable accuracy. His equations could predict the motion of planets, the fall of an apple, and even the trajectories of comets with stunning precision. However, small discrepancies remained, particularly in the orbit of Mercury, the innermost planet of our solar system. These anomalies puzzled astronomers and physicists alike, as Newton's laws couldn't fully account for them. It was Albert Einstein, in the early 20th century, who provided a new and radical understanding of gravity, one that would once again revolutionize our view of the cosmos. His insights would challenge the very foundations of classical physics. Einstein's theory of general relativity, published in 1915, proposed that gravity is not a force acting at a distance, as Newton had posited. Instead, it introduced a groundbreaking concept that would change our understanding of the universe. Instead, it's a consequence of the curvature of space-time caused by the presence of mass and energy. This idea was revolutionary, suggesting that massive objects could bend the very fabric of the universe. Massive objects like stars and planets warp the fabric of space-time around them, much like a bowling ball placed on a trampoline curves the fabric. This warping effect is what we perceive as gravity. This curvature then dictates how objects move within this warped space-time. Planets, stars, and even light follow paths determined by this curvature, leading to phenomena such as gravitational lensing and the precise orbits of celestial bodies. One of the first and most compelling validations of Einstein's theory came from the planet Mercury. Astronomers had long puzzled over a slight anomaly in Mercury's orbit. Its perihelion, the point in its orbit closest to the Sun, shifted slightly more than predicted by Newton's laws. This discrepancy, though small, was a thorn in the side of classical physics. Einstein's General Relativity provided an elegant solution. The warping of space-time by the Sun's massive gravitational field precisely accounted for the observed precession of Mercury's orbit. This successful explanation of a previously unexplained phenomenon was a major feather in the cap of general relativity, demonstrating its ability to account for gravitational effects in strong gravitational fields. Another key prediction of general relativity was the bending of light by gravity. According to Einstein's theory, the path of light, though massless, should be deflected as it passes through a strong gravitational field. This prediction was dramatically confirmed during the total solar eclipse of 1929. Astronomers observing the eclipse found that the apparent position of stars near the edge of the Sun was shifted slightly, precisely as Einstein's theory had predicted. The bending of light by gravity, a phenomenon now known as gravitational lensing, became one of the most iconic validations of general relativity. It demonstrated that even something as ethereal as light was subject to the warping of space-time caused by massive objects. From the Earth-centered cosmos of Ptolemy, where the universe was thought to revolve around our planet, to the revolutionary ideas of Einstein, who introduced us to the concept of warped space-time and the bending of light by gravity, our understanding of the universe has undergone a profound transformation. Each discovery has built upon the last, creating a more intricate and detailed picture of the cosmos. This journey, driven by curiosity, observation, and the relentless pursuit of knowledge, has been marked by countless hours of research and observation. It stands as a testament to the power of the scientific method, which has guided us through centuries of discovery and understanding. It reminds us that our understanding of the universe is not static but constantly evolving, subject to revision and refinement as new data and insights emerge. As we delve deeper into the mysteries of the cosmos, we uncover more questions, leading to further exploration and discovery. With advanced telescopes and space observatories, our ability to explore the universe with ever-increasing sophistication has grown exponentially. We must remember that the quest for knowledge is never-ending. Each answer we find often leads to new questions, propelling us further on this infinite journey. The universe is full of wonders, and each discovery, each new insight brings us closer to understanding our place within this vast and awe-inspiring cosmos. As we continue to explore, we gain a deeper appreciation for the complexity and beauty of the universe. We must embrace the spirit of scientific inquiry, always ready to question, to explore, and to seek out new knowledge, to question, to explore, and to marvel at the wonders that the universe continues to reveal, pushing the boundaries of our understanding. The journey is without end, and the universe, with all its mysteries and wonders, awaits our continued exploration and discovery. And now, I'd love to hear from you, but what do you think was the most fascinating part of this journey? Was it Kepler's mysterious ellipses, Newton's apple moment, or Einstein bending space and time? Share your thoughts in the comments below. I always enjoy reading what you think. If you enjoyed this video and want to explore more stories about our universe, don't forget to like, subscribe, and hit that notification bell so you don't miss what's coming next. Thanks for watching, and see you in the next one.